Perfect. Okay. So it is 8:35 now, so I guess we'll get started. Thank you guys for attending. I know it's not easy waking up this early on a Friday morning, so really appreciate it. So today we're going to go over CNN basics. Last lecture, you guys should have already started going over CNNs. We're definitely not trying to replace Professor Raj's slides and lectures, but this might help you get a little bit more background on CNNs and learn more about the basics of how to propagate forward and also how to backpropagate. So let's discuss what you guys have learned so far. So you guys have learned about a perceptron. So that's like a single neuron, and how we can design a perceptron to linearly separable data. We've also learned about simple MLPs and how these MLPs can detect certain patterns. And we've also learned about backpropagation and how to apply this backpropagation for gradient descent to update weights and biases. But there are a couple of things that we need to get some clarification on. So what exactly are the pitfalls of just a simple MLP? What is a scanning MLP? So I think you guys went over that in the last lecture. What is a CNN? What are some of the specific terminologies related to CNN? How does the forward function of a CNN work? We also want to go over some downsampling techniques, and then we also want to give an introduction to backpropagation. So I believe you guys went over this in lecture, but basically with the MLP structure that you guys had learned previously, it was very location specific. So for example, you guys were looking at detecting if a point was in a specific pentagon in a certain region in the XY coordinate system. And so it was very region and location specific. But when we're looking for like a pattern or a word or like a specific image within an image, we don't want it to be location specific. So for example, if we're looking for the words Harry Potter in an utterance, suppose it comes in the 5th second of an utterance, but in another utterance, it might come in the 10th second, or it might come in the 2nd second. So what happens if the word appears somewhere else? The same goes with images, right? So for one image, the dog might appear in the middle of the image, but for another image, it might appear at the corner of an image. And so we want our network to output that there is a dog. We want our network to output that Harry Potter does exist, no matter where the pattern exists. I hope that makes sense. So basically, at the end of the day, it's not the location of the pattern that's important, but the fact that the pattern even exists in the data that we're looking at. And so that's why we're scanning an image or scanning an utterance for a pattern. And so this scan would be considered 1D for sound, and it would be considered a 2D scan for images because you have both a height and a width. And so you would want to scan across the entire image or scan across the entire utterance to find the pattern, because you want to look at every possible instance to see in this frame, does the pattern exist? In this frame, does the pattern exist, et cetera, et cetera. And so you can see in this image, we're scanning the entire image left to right to find out if a dog exists. And so I believe that you guys saw this in lecture as well. So you can think of this as having multiple MLPs of this same exact type, just scanning the entire utterance or scanning the entire image with this single identical MLP. And the MLP will either output a 0 if the pattern does exist, or a 1 if the pattern sorry, a 0 if the pattern doesn't exist, and a 1 if the pattern does exist in the frame that you're looking at. And so if you take the max of all of that, you're going to be taking the max of a bunch of zeros and potentially like a couple of ones. And so the max will either give you a 0 for there was no pattern detected, or a 1 for there was a pattern detected at some point. I hope that makes sense. So just to reiterate, you use the same MLP throughout the entire utterance or the image as you're scanning it. And for the most part, in the majority of the places, it's going to say there was no pattern detected. But if there is that image or that word or that utterance that you're looking for, or that pattern that you're looking for, the MLP will produce a 1, meaning that that pattern does exist in the frame that you're looking at. And so when you're taking the maxes of all those zeros and that 1, 1, it's going to output a 1 because 1 is more than 0. I hope that makes sense. So let's talk about the images that we're going to be dealing with. So I'm sure all of you guys have heard of RGB images. So RGB is called RGB because it stands for red, green, blue. And that means that there are 3 different channels for RGB images, one that deals with how red the image is, one that deals with how green the image is, and one that deals with how blue the image is. So you can think of RGB images as basically just images that manipulate the amount of redness, greenness, and blueness in an image. And so each channel deals with one of those colors. So for example, this channel is dealing with the red hues and colors. This one's dealing with the green ones, and this one's dealing with the blue ones. And so if you think about it, when we're dealing with one image input, we're actually dealing with 3 different channels, and in a way, 3 different inputs, because we're dealing with the red, green, and blue. And when we're dealing with black and white images, we actually only have 2 channels, and that would be the black channel and the white channel. And each channel, for each pixel, you have a different value to it. So for example, for this pixel, 35 is relatively high compared to the other values. So the redness at this pixel value is going to be a little higher than at the other pixel values, and even higher at this 53. I hope that makes sense. So just to reiterate, when we say the number of input channels, we're referring to the number of like color channels. And there are some cases where you might face more than 3 channels, but for this class, you'll just be working with RGB images, which just have 3 channels, which is red, green, and blue. Okay, I see someone has asked something on the chat. Let me see. Why do black and white images have 2 channels? That's because you have a channel for black and you have a channel for white. And so you're just manipulating the different pixel values for the amount of blackness and the amount of whiteness. Okay, I'm going to move on. So let's get to some specific terminology when it comes to CNNs. So when we're dealing with CNNs, we have a filter. And if you look at the graphic above, you'll see that we have this 3x3 filter that we're scanning the entire image with. And so that's basically a set of weights that we're scanning the image with. And that's what we're going to be trying to learn. That's what we're going to be updating through backpropagation. And we're going to look at the next slide and see how exactly these weights are applied. But for the time being, you guys can think of the filter or kernel as like the set of weights that we are using to scan throughout the image or the utterance in order to detect a pattern. And when we refer to kernel size for this class, our kernels are going to be a square. So when we refer to kernel size, we're just talking about the length of a side. So in this case, the kernel size would be 3 because this is a 3x3 square. The stride is the amount by which the filter and kernel moves. So for this example, each time we're moving the kernel, we're just moving by a stride of 1 to the right. And then once we reach the end of the image, we go all the way back to the left and move down 1 stride. So I hope that makes sense. So we're just moving 1 to the right each time. And then once we've reached the end, we go back to the left and move 1 down. There are multiple cases where you have a bigger stride than 1. And in that case, we'll need to use padding, which we'll get to. But you can have a stride of 2, 3, et cetera, et cetera. But in this case, we just have a stride of 1. The input channels, that's the number of channels in the input. So we already kind of talked about that. So for RGB images, it would be 3. And then the output channels, you can basically consider that the number of filters we're applying. So this is 1 filter here, but we're going to have more filters to do more pattern detection, right? And so each of those filters is going to output a different output. And so the number of output channels you can easily think of as the number of filters applied. So padding is basically what you want to add to the outside of the image. If your stride is greater than 1, you want to do this because when you're applying your filter, you want to make sure you get all of the pixels. You want to make sure that you're doing some sort of manipulation with your kernel with all the pixels in your image. And it is possible that if your stride is greater than 1, your kernel will basically go off of the image. And if there's no padding, it can't really go off of the image. So we'll talk a little bit more about this later. But for now, you guys can think of padding as just a necessity if the stride is greater than 1 and there's a possibility that the kernel will go off of the image and thus we won't be able to convolve all of the pixel values. And so this is a very useful formula down here if you want to get the output size. So the green thing here, that would be our output. So if you want to get the size of this, you can use this nice formula. So the width and height of our original image, as you can see here, is 4. It's a 4x4 image. The kernel size is 3 because this is a 3x3 kernel. And then we have 0 padding, which is very possible. So we do 4 minus 3, and then our padding is 0, which is very possible. We don't always need to have padding. So then we get 1, and then our stride is 1. So we get 1 divided by 1. And then we get 1 plus 1. So our output size is 2. And if we look at our output, it is a 2x2 square. And so you can use this formula, and you probably will be using this formula for your homeworks to decide exactly what your sizes are going to be based on your hyperparameters such as padding and kernel size. So let's talk about exactly what is going on when we're applying the kernel to the image. So here we have a pretty nice graphic that kind of shows what's going on. So let's imagine that our filter is this 1, 0, 1, 0, 1, 0, 1, 0, 1. And you can see that resembles the red numbers that are being like moved throughout the image. So let's see if there's a way I can pause this. Can I pause this? I don't think I can pause this, Jeff. Basically, we'll be applying this to each time we scan a section of the image, we're going to be applying these weights to the values at that specific area in the image. So for example, let's imagine the yellow region is here, right? In that case, we'll be doing 1 times 1, 0 times 1, 1 times 1. I'm just reading off the filter here and reading off the values here. So then it'd be 0 times 0, 1 times 1, et cetera, et cetera. And so you get all those values and you add them up and you get 4. So as you can see, there's kind of a description down here. If the image is going too fast for you, you basically just multiply the respective values together of the weights and the image. And then you add all those values together to get your value, corresponding value in your output. And so you continue this trend throughout your entire scanning of the image. And so, for example, once we move the yellow rectangle to like this area here, we get a different value because the values of the image is different, yet the values of the filter remain the same. Does that make sense to everyone? Okay, I'm going to take that as a yes, but please ask questions in the chat if you have any questions. Okay, cool. Someone said yes. Okay, cool. So when we're dealing with multiple channels, you can actually think of the kernel as like a 3D weight matrix, right? And we're using this 3D weight matrix and scanning it throughout all the channels. And then we actually like add all of the respective outputs together to get our final output, which is one single channel that corresponds to one single kernel or filter. And so I think this is a really nice visualization that kind of shows you how you can think of the kernel as 3D and your input also as 3D. And you're just scanning this 3D kernel along your 3D input. And so like I said before, the number of kernels you have or the number of filters you have, that equals the amount of output channels you have as well. So this is like another nice visualization. You'll be scanning, like I said, these weights along the image, and you can think of them as like 3D scanning. So yeah, just something to keep in mind, number of kernels equals number of output channels. I think there's a question. For 3 channels, are the weights the same across the channel? Yeah. Okay, and now let's talk about padding. So padding can be seen as these zeros. So this is the original image here. And these zeros that are around the image are the padding. And this padding is really, really crucial if you have a stride that's higher than 1 and your kernel is going to go off the image. So for example, let's imagine that our kernel size is, not our kernel size, sorry. Let's imagine that our stride is 3. So if our stride was 3 with just our original image, so just ignore the padding right now. If our stride was 3 and our kernel size was 2 by 2, we would start here, right? And then a stride of 3 would actually go to here. But if there was no padding here, there's no way like our kernel could have moved to here. Does that make sense to everyone? Okay, I'm going to take that as a yes, but please comment in the chat if it doesn't make sense. Rukayat is here as well, and she can answer questions. Okay, it does make sense. Cool. So, and that's why we add padding. And so now when we add padding, if our stride is 3, we move here, and that's not considered off the image anymore. And so padding is pretty crucial if you have a high stride. And padding is like one of those hyperparameters that you're going to have to play around with when you're tuning your model for your part 2 homeworks to see what type of padding is most effective. So next we're going to get to downsampling. So once you've done your convolution, once you've applied your weights, your filters to your image, and you get all your values, you might want to reduce the number of parameters you're dealing with, or you might want to like reduce the noise that you're dealing with. And so there are different types of downsampling methods or different types of pooling methods that you can use to do this. So we'll go over the 3 main ones. So one is max pooling. So max pooling is basically where you look at different regions of your image. So for example, here we're looking at a 2x2 region. And unlike when we were doing, when we were using our kernel, where like we had a stride that like might have made some like convolutions overlap with others, these like are separate regions. So you want to divide these regions up like separately and like they don't overlap with each other. So if we have a 2x2 max pool, we would divide it up like this. So each region is by itself and doesn't overlap, right? And we look at each region, and for max pool, we take the max value of that region. So for example, for this region, the max would be 20. For this region, the max would be 30, and so on and so forth. And so what this helps us do is that it helps reduce noise, and it just also helps reduce the number of parameters you're dealing with, because here we're dealing with 16 values, whereas here we're dealing with 4 values. And min pooling is exactly the same as max pooling, except that you're taking the minimum value. So instead of taking 20 in this red region, you would take 8. Instead of taking 30, you would take 0, et cetera, et cetera. So I hope that makes sense. And then for average pooling, it's the same logic where like you have separate regions of your image, but instead of taking the min or max, you just find the average. So for a 2x2 average pooling, you would add all the values within an area, and then you would divide by 4 because 2x2 equals 4. So you're dealing with 4 values. So for example, this region, you would do 2 plus 2 plus 0 plus 0, and then divide that by 4. So you get 1. And then here you do 2 plus 4, which is 6, 6 plus 6, which is 12, and then 12 plus 8, which is 20, and divide that by 4. So you get 5. And so you can continue doing that type of math for all the regions, and you can reduce your output size substantially. So that's all I have for now. Rukaith is going to go over backpropagation. And then later we're going to go over like a notebook with some helpful functions. But do you guys have any questions about what I just went over? And okay, so I see some questions on chat. So we need some dimensional correctness to perform convolution, which is why, yes, exactly. So we need padding basically to make up for like having, if we have a big stride, we need the padding in order to make sure that like our kernel doesn't like go off of the image. Using multiple filters equals to the concept of distributed learning in the lecture. I'm not sure about that. Using multiple filters basically refers to like having multiple different types of like convolutions and weights that you're using to like find patterns. So it doesn't really make sense to just apply one convolution, right? There isn't much you're going to get from applying just one convolution. So you want to do like a combination of convolutions and a combination of weights to find patterns. In what situations would we choose a stride size greater than the kernel size? Yeah, I don't think you would actually do that in the real world. Usually the stride would be smaller than the kernel size. For 3 channels, are the weights the same across the channels? So if you're dealing with one filter and you're applying that filter to the 3 channels, then yeah, that filter is going to be the same across all the channels. But obviously you're probably going to be dealing with like more than one filter. So like you might be dealing with 4 filters. So each time you apply that filter is going to be the same for each of the channels. Okay, cool. I don't see any more questions, so I'm going to hand it off to Rakayeth. Thank you, guys. Rakayeth, if you're speaking, you're on mute.
Yeah, can everyone hear me now?
Yep, you're good.
All right. Welcome to the second part of the recitation. In this part, we'll be talking about the CNN backprop. I don't think this has been touched yet in class. In the coming week, you'd cover this, but we thought to cover this now, especially since homework 2 has been released, and this segment of the recitation would be very useful in homework 2 part 1. So remember, generally when you go in the backward pass, you're trying to get the loss gradient with respect to the next layer. But then in CNN, it's slightly different. You have to get the loss gradient with respect to the input and the filter, because like Omisa has said, you have your input image, and then you have a kernel, a filter. Kernel and filter are used interchangeably. So you have your kernel or your filter, both of which are passed into your network, and then it goes through the layers till you get to the output. So you have to get your loss gradient with respect to the input and also with respect to the filter. We'll first consider a situation where you have a single stride and then more than a stride greater than 1. So given a 3x3 input and 2x2 filter, when we're trying to do a backpropagation, first we need to do the forward pass. So we'll quickly refresh our heads with the forward pass. The forward pass is basically a convolution operation between the filter and the image, and the input matrix and the filter, the kernel you've passed in. And when you convolve this, you would have an output size, an output or a feature map that is oftentimes the same size as the size of the filter. So basically, I'm not sure if everyone knows what a convolution operation is, but what this means basically is, okay, this might be a bit confusing looking at so many things moving at once. So I'll just explain here first before I move on to the next slide. What this means is we take this filter, place it on this input, perform a convolution, and then slide. Here we're using a stride of 1, so we slide 1 step and then perform it on this operation, on this set of inputs, and the same thing, we move down here and do the same. So what happens when we're when we place the filter on a section of the image? What we're basically doing is, say say we put our filter here, what we're basically doing is we're saying x1 multiplied by f1, x12 multiplied by f11, x11 multiplied by f11, x12 multiplied by f12, this multiplied by this also, x22 multiplied by f22, and you sum up all the multiplication. That gives you the result for the first output. For the second one, when you slide one step, or depending on the number of strides you set, you would sum up the multiplication of each element with the element of the filter, and the summation would be what you have here. So basically, okay, my slides are not moving. I'm a bit lost. This is weird. Okay, so that's basically what this GIF is saying. Place the filter over each section of the input, and then you get your corresponding output for that section. So when you convolve the entire the input and the filter here, you get something like this at the end. So your output size would be a 2 by 2, and this would be the value of your output size, or your output matrix rather. So that's the forward pass. So remember that what goes into, remember that what goes into your convolution is the filter and the input matrix, and what comes out is the output of the convolution, right? So if we wanted to, yeah, I need to post this. Just a second. I need to pause the animation so you can see what's going on. Yeah, so when we take the loss gradient from the output layer and we try to backpropagate, that's what we're looking at now. So remember I said at the beginning, the CNN backpropagation, in CNN backpropagation, you take your loss gradient with respect to both the input and the filter. So that's what we're going to be doing now. So first, we consider the loss gradient with respect to the filter. So this is from the previous slide, we can see we have the LDO, right? And we're trying to find the LDF. So from our chain rule, we know that we can easily do this. We can easily do this. Trying to annotate. Just a second. So we can easily do a chain rule operation on the gradient with respect to the previous layer, which in this case would be if we had like if we had like just one, we had the input, the output, and the input, the filter, and the output. We would have the previous layer would be the output layer, right? So the loss gradient with respect to the output multiplied by local gradients. What do we mean by local gradients? Remember from this previous slide, we calculated the outputs as a function of the input and the filter. So we can say that we can find D of O at 11 with respect to X and with respect to F. And basically, if we try to find, for the first equation, if we try to find the output with respect to, say, the filter at F11, the gradient would be X11. Same thing if you try to find if you try to find the gradient with respect to x11, you'd find you get f11. So sorry, that's basically what we're saying here. And basically, because it's a matrix, you would do an element-wise chain rule operation and sum it up to get the gradient with respect to the entire filter. So yeah, so when you expand this summation expression, you get something like this. And remember that I had said from this slide, from the previous slide, you can get the operations for the gradient of the output with respect to the filter, right? We can get it from this equation. So if we decide to make substitutions, if we decide to differentiate that equation and substitute the value, we'd get something like this, right? And this basically, if you take a look at this, it basically means that you're trying, it's similar to a convolution operation that we saw from the previous slides, but in this particular case, we're trying to perform, it feels like we're trying to perform, to find the gradient the loss gradient with respect to the filter. It feels like we'll be making a convolution operation between the input and the loss gradient, the actual loss gradient. Does anyone have any question at this point? I'm just looking through Slack. Okay, Misa is attending to that. If you don't understand anything, please feel free to stop me along the way and I will go back. So that's generally the way to find the gradient with respect to the filter. Now, with respect to the inputs, you basically have the same formula like we had for the filter. You take, you do a partial derivative between each element of the loss gradient and the local gradient, and you sum them up. That'll give you the loss gradient with respect to the filter. And just like we expanded the previous one for the filter, when you expand this, you might have to take a pen and paper to expand this, but if you follow this animated operation here and you expand the previous, the equation in the previous slides and make your substitution, you would get, you get this. So we're trying to establish a relationship between, just like the way we established the relationship between the filter and the gradient, the loss gradient with respect to the filter and the input. We want to establish an expression for this. So if we look at this expanded equations carefully, we would see that assuming we had this filter and we flipped it horizontally and vertically, or you can choose to flip horizontally first and then vertically. You can choose to flip vertically first and then horizontally, so long as you make a complete 180 rotation. So you flip in one direction, in the left direction, and then upside down. When you're using NumPy, you have something like a flip UD, I think. There are multiple flip operations for matrices and NumPy, so you can check that out when you're doing your homework. So first, you imagine you flip your filter by 180 degree, and then you perform a convolution on it. But this convolution is slightly different from the convolution we had in the forward pass and in the gradient with respect to the filter. This is called the full convolution. So you're basically sliding through the edges and moving. I really can't pause this particular animation, but you can take your time to observe the pattern afterwards. So you slide, you're taking the gradient across the corner and you're sliding across it. You're passing, you're sliding the matrix of the loss gradient across the filter at different corners and getting the corresponding expansion. And so the LDX, which is the loss gradient with respect to the input, would be a full convolution of the filter with the loss gradient. Remember that for filters, which we first of all covered, the loss gradient with respect to the filter would be a convolution of the input and the loss gradient. And then the loss gradient with respect to the input X would be a full convolution between a 180 flipped filter, a 180-degree flipped filter, and the loss gradient again. I hope this makes sense. Ryan is asking, why do we flip the filter? We're trying to find, it's kind of like we're trying to work our way backwards. This is the expression. This is the expression to find, the gradient with respect to the inputs, right? But we're trying to find a compact formula for us to use. And it's like we're working our way backwards. Upon observing this, we see that the only way we can actually get a convolution operation that translates to this is when you flip the filters in the vertical direction and the horizontal direction, basically through 180. There might be another explanation, but that's the explanation I can give you for now. I can give you an updated explanation on Piazza later. I hope that addresses it. So yeah, so that's a summary of how to find the gradient with respect to the filter and the inputs for a stride of 1. But for the assignment, you'll be working with a stride of 1 and also situations where your stride is not 1. So what do you do in a situation where your stride is not 1? So imagine we have this, as the input, right? It has a height of h, and so this is a 2D input. It has a height of h and a width of h. So it's a 5x5 input. And then you have your kernel or filter as a 3x3. Now, the stride here is, I believe the stride is 2. I think yeah, okay, it's written here. It's a stride of 2. So what that means is, in this particular situation, sorry, I mistakenly stopped sharing. So in this particular situation, what that means is we take our filter and place it against this section. We perform a convolution, then we slide it 2 steps. We slide through a window of 2 because the stride is 2, and then we perform the next convolution from this point, right? And then when you perform that convolution, you save the results here. The first one is saved here, and you slide again vertically by 2. And so your next convolution would be between this section of your input with the filter, and then you slide again by 2 to get your final Y element. And so that's basically how you would work with a stride of 2. So yeah, that's basically what's been explained here. You slide 2 steps horizontally and vertically, and you get this. And the equation has been expanded as you go if you watch the animation carefully. So how do we calculate the loss with respect? Again, in CNNs, you calculate your loss with respect to both the input and the filter. How do you go from here? Remember that your output matrix, your output matrix is now a 4x4, right? How do you go from this back to something like this, but the gradient, the loss gradient with respect to the input? So to do this, so there's some assumption made some assumptions. We have the loss gradient with respect to the output, that's this. Just a thing to note, in the first section, I was representing the output as 0. In this section, in this situation where we have stride of 2, I'm representing the outputs with Y. So please don't be confused. And yeah, so how do we do the backward pass in this case? It's basically the same formula as we had from, I'm just going to quickly throw us back there. It's similar to this formula. Similar to this formula here, where we have a summation over the partial derivatives between each element, between the loss gradient and the local gradient. So the letters, the notations have just differed a bit. So back to the stride of 2. So in this case, Y is the same as 0 from the previous equation, and X remains X. X is the input. So you find the partial derivative and sum up all the partial derivatives, right? What that means is, we want to consider the inputs. We have the 5 by 5 matrix, right? We can see that in this case, X at this point, the yellow box, contributes only to the output at Y00. When you slide with a stride of 2 and come and perform a convolution again, there's no place that X at 00 features in the convolution operation. So what that means is that you take a derivative with respect to the derivative of Y with respect of your output with respect to the input at that particular index, and this is the only thing you get. Sorry, you get the value highlighted in red. That's the point where X00 is contributing to the output. So when we differentiate this, every other thing every other things don't matter because we're doing a partial derivation. So those don't matter, just the part that is highlighted in X. And when we differentiate that, we have F00. And remember that we're doing a partial chain derivative. So we multiply that with the loss gradient of the output. And so we get the Y dx at that particular input index. So that's the same way you step through all the other elements of X, and then you look through to see where how many times each X element contributes to the output. In this case, so in the first 2 cases, they only contribute to the first output. X00 contributes to the first output, X01 contributes to the first output. But when we slide with a stride of 2, X at 02 contributes both to the first input, the first output and the second output, right? So that's why the partial derivative for the loss with respect to that particular X input would be a sum of what you have from the first output and what you have in the second output. Make sense? So you go through it all the way. If you observe this closely, the only elements that really contribute to all 4 outputs would be X at 2, 2, 2, right? So that's why the loss gradient with respect to X at 2, 2 would have 4 elements in its summation. And yeah, so when we have this, what do we do next? Yeah, so remember that I'm trying to get back to that slide. from this animation, we had this 5x5 input and 3x3 filter, but because we had a stride of two, a stride of two, the output size reduced drastically. If you plug in the dimensions of the input, the stride, the kernel size into the formula that Omisa had shared earlier, you would see that the output would actually be two. You can try that at your free time. So we just can't perform the same operation we performed when we had a stride of one, because we wouldn't get the exact input size back. So what do we do in this case? So that's when we have this, that's our dilemma, right? So that's when padding and dilation comes in. So basically the rule is to pad all the edges. So the goal, what we're trying to do basically is we're trying to expand the output map. We're trying to expand it such that when we perform a convolution on it, it would give us back the size of the input map, something like, of the input matrix, something like this, right? So how do we do this? We pad all the sides with the size of the stride. So that's why we have 0 zeros on the side. Then we dilate the in between the inputs. What that means is we try to expand the, what's it called? We try to expand in between the inputs, the loss gradient matrix itself. We try to expand it with stride -1. And so on the outside, we pad with the size of the stride. On the inside, we dilate in between the matrices with stride -1. So that's why we have 1 zeros cutting through the matrix, the output matrix, the loss gradient matrix. And we have 2 rows of zeros padding all sides of the output gradients. I hope that makes sense. So we kind of expanded the loss gradients. We kind of expanded it so that we can then perform the operation on it, the backward pass operation on it. So what do we do next? It's basically the same thing we've been doing all along. You flip vertically and then horizontally, basically a 180 flip. Someone is asking what's R in the image and wasn't our stride 2? So why should we pad the outside with 1 cell? So if we go back here, R is the height of the filter, right? And S is the width, right? So so back here, that's my error actually. You pad with the size of the kernel of the filter -1, right? And I think this part is a typo. You pad with padding size of -1, and then you dilate with stride -1. Does that answer it? Okay, looks like it's clear. So basically, we just do the same. Now that we've expanded the loss gradient matrix, we can then perform our convolution, backward pass, which is also a convolution, if you remember from the first summary. But first, we need to flip vertically and then horizontally, and then we do the same operation that we had before. And so you can see from the animation, you're basically convolving the expanded matrix by the filter to get the inputs. Remember, to get your inputs, you to get your inputs, to get the loss with respect to the input, you convolve the filter with the loss with respect to the output. And for your sorry, I didn't have a slide for the other one. And for your loss with respect to the filter, you convolve your outputs. You convolve your sorry, for your loss with respect to the filter, you convolve your input matrix uh, with respect to the loss of the output. But remember that for the loss with respect to the output, you first have to flip your filter 180 degree and then you perform a full convolution, if that makes any sense. So basically what this is telling us is that when you're convolving with a stride greater than 1, it's basically the same stride operation, but the output map shrinks. And that's why we see that from here when we convolved, just try and get back to that slide. When we convolved this with a stride of 2, the output map reduced, right? So any convolution with a stride greater than 1, you expect not to have the same output size as your filter. And in that case, you would have to expand. You have to expand before you can do your backward pass. That expansion is is what we call upsampling. And yeah, there are a few more slides, but I think we pretty much covered it. Oh, okay, so this is the loss with respect to the filter. I thought I skipped this. I thought I omitted the slides in the presentation. So it's basically the same thing, but in this case, it's the same formula, but in this case, you would only dilate. You don't pad. When you're trying to get your loss gradient with respect to the filter. You don't pad. You only dilate the output gradient for you to be able to get your filter size back. I hope that makes sense. And you basically perform the same convolution operation, and then you'll be able to retrieve your loss with respect to the filters. And yeah, the backprop operation is basically similar when stride is greater than 1 or stride is equal to 1. The only thing is that when you use a stride greater than 1, your output map reduces, the output size reduces, and so you would have to upsample your gradients before you are able to do your backpropagation operation on it. So yeah, these are references you could visit to learn more about backprop with CNN. Ryan is also asking, how is this a dilation of S minus 1? I thought S was 3. Let's take a look again. So I said, it says S stride minus 1. So let's go look at what S stride is again. S stride is 2. The stride is 2. The stride is 2, not 1. The stride is 2, not 3. Those are two different things. S stride is different from S itself. So, sorry, stride S is different from S itself. So, you expand, you only dilate the output gradient for the loss with respect to the filters. So if you have any questions, I'll hang around to take your questions in the chat. But Omisa, I'll be walking you through a notebook that would help with some other sections of your homework too.
Okay, awesome. So can you guys hear me?
Yes, we can hear
Okay,
you.
awesome. Okay. So this notebook goes over basic functions that you might be using to make a CNN for your homework 2 part 2. In the homework 2 bootcamp, you guys will go into more detail, but I think that this notebook is a really nice like intro to CNNs using PyTorch. So as you can see, 2D data should kind of look like this, where it's number of samples, number of channels, and then your height and your width. And then your 1D data should be the samples, the number of channels, and the amount of time. So it's not 2D, so you don't have like a height and width, you just have like a time. So for example, in these two situations, they're kind of just making like a random input image. And you can see that there's one sample, there are 3 channels because it's an RGB image, and then the height and width is 32. And then here there's one sample, there are 40 channels, and the time is 100. Here's an example of a convolution in 2D. So as you can see, the number of in channels is 3 because RGB. Number of out channels is 20, so that means you are applying 20 different filters. Your kernel size is 5, your stride is 1, and then padding is 2, which means you have padding of 2 along the width and the height. So if you look at the results of applying the convolution, you get this size. And if you apply all like these numbers into the formula we gave you, you'll probably get these numbers as well. Not probably, you will get those numbers as well. And as you can see, with all these 2D convolutions, as you increase the padding, your overall size is going to go up because basically you're giving a bigger image input, if that makes sense. So the more padding you have, the larger your output will be. So yeah, this torch.nn.conv 2D is a really good function to know. You'll be using that a lot. These functions you'll be using for downsampling. So this is average pooling. We talked about that before, where you're averaging a section to downsample the data. And then you also have max pooling. And then you can also use dropout in CNNs as well. And you probably want to use stuff like dropout and batch norm in CNNs to, help strengthen your model. So those are good functions to keep in mind as well. And like we talked about downsampling, you might have to do some upsampling too. You're probably not going to have to use all of these functions, but I think this is just like a good document to read over. There's some good like links to like animations that can help you walk through what exactly is going on when you're doing convolutions. So I would definitely recommend looking over that. Yeah, you guys won't have access to these images, but I think it's good to see how exactly, if you do have an image, how to like see it, how to show it, using pill. This this part is pretty crucial. So you guys are probably going to be using image folder. Image folder is basically a way to make your data set of images. And you guys will be talking more about it in the homework 2 bootcamp. But basically, once you've like unzipped your data and like you've parsed your data, you're going to want to pass your data into image folder, and you're going to want to put some transformations to it. So Torch Vision has like a bunch of different transformations that you can use. One is like random horizontal flip. Another one is random vertical flip. So basically what those functions do is that they randomly like flip the images vertically or horizontally. And you want to do that kind of to strengthen your model and to let your model see different instances of images so it can better generalize in the real world. And so there are other functions that you can also use. I believe there's one where like you can rotate the image a certain amount of degrees. So you'll have to play around with like different um, image augmentation functions and see which ones work best to train your model. But here are a couple. You definitely will need to add this transforms dot to tensor because your model is going to accept a tensor, not a pill image, because your model accepts numbers, right? It doesn't accept images. So yeah, you'll go more into that during the Homework 2 bootcamp, but maybe start researching like image folder and like the transform functions in Torch Vision that you can apply um, to images. And so image folder helps you make your data set. And then once you have your data set, you can pass it into the data loader. And yeah, so you can make different models once you have your data set. So for example, here, you first do a convolution, then you downsample with like a max pool. Um, in your homework 2, part 2, you're going to be making a ResNet. Um, and like I've said a million times before, they'll go more into that during the boot camp. But you'll basically be having to use like a combination of convolutions, of downsampling techniques, and linear layers to make your ResNet. So it might look something like this. And yeah, uh, your training method is going to look similar to something like you saw in homework 1 part 2. Uh, if you guys didn't know, this is a good way to save your model, your optimizer and scheduler. Please do this if you're using Colab because your web browser might, crash and you'll need to uh, somehow load your model, optimizer and scheduler again. And this is how you load all of those back up. So yeah, I would take a look through this sorry, not network, this notebook and go through some of the functions. If you have any questions about any of the functions, let us know. But I think that's all we have for you today. Let me look through the chat. Okay, I think you guys were talking among each other. um, yeah, but I think that's all I have today. Yeah, thanks for coming again. Hope you guys found this helpful. And happy Friday, guys. No worries. No, you're not allowed to use pre-trained models.